are in Generalized Linear Models with Examples in R, book right there in Chapter 4, and we're just on the second question here. And this ended up being a very long answer, and maybe we'll see why here in a little bit. But here's the question. So in the book, there's an example 4.10 in which the information matrix was given for a Bernoulli model fitted to the Quilpie rainfall data set. Okay, and then the result from that example, which is equation 4.5 or whatever, result 4.15, we're meant to prove that. Okay, which I take to mean just basically deriving it. So what I've done here is I've recreated example 4.10. Okay, so I'm not going to go through all of this. This is basically just what's in the book. But importantly, what we get out of okay, so what we get out of this is not, so 4.15 is not in this. We actually have to scroll down. So not only did I create example 4.10, but I also had to recreate example 4.11, and both of these are used en route to 415 right here. This is what we're meant to prove right here, or I take that to mean, demonstrate how how we can derive that. Okay. So all of that is, basically just paraphrased from the book, or taken from the book, so that you don't have to go back and look at it. You can just read through this. But what we want to do is to come out with the information matrix here. Okay, and I'm also going to just kind of continue that to the Fisher information matrix, which is the expected value of this information matrix. But here it's just the same. But that's fine. Okay. So what are we going to do? So first, I'm just going to make sure that we're clear on what the variable is, y here, okay, and it's 1 or 0, and 1 is whether or not rainfall in July exceeds 10 millimeters, okay? So this is a Bernoulli random variable. It's 1 or 0, and it will be 1 with some probability, p or mu. Here I think I'm using mu as that parameter, okay? Now, so let's say, okay, so let's start with a simplified example where we just have mu, right? So we're just trying to find mu here, okay? How does this differ from what we're meant to find? Okay, what we're meant to find is the information matrix that has two parameters, beta naught and beta 1, okay? So because we have two parameters, we end up getting this 2 by 2 matrix, okay? So just as a simplified version of this, we're just going to start with one parameter, mu. So now there's no, the information matrix is just 1 by 1, okay? It's just a, one value, okay? So, but let's just walk through the steps of getting to the information matrix, okay? So, we start by writing our probability function here, okay? So this is our probability function for a Bernoulli random variable. And then we take the likelihood, okay, of all of our data, and the likelihood of all of our data is just the product of each of the probabilities, for each observation, okay? And ultimately, we're going to have to take the derivative of all of this, and because this derivative can get gnarly, it's much easier to use the log likelihood, okay? So if we take the log of this guy, then products turn to sums, and then just following your logarithm rules, we come out that the log likelihood is this right here, right? So the log of mu to the y, so the y just gets knocked out to the front, and then we have the log of mu. I'm using natural log, okay? And then similarly, 1 minus y gets knocked out front, and then we have the natural log of 1 minus mu, okay? So there's our log likelihood. And now en route to our information matrix, which is just the negative second derivative of this guy, we need to get the first derivative, and that first derivative is called the score function, okay? So, and in the book here, it's typically denoted with this uppercase U. So we have U of mu, okay, which is just the derivative of the log likelihood with respect to mu, okay. And so if we take the derivative of our log likelihood, okay, we come out with this. This is the final expression, or okay. And then we want the second derivative, and then the negative second derivative is the information matrix, okay. And so now if we just take the derivative again of this guy, you can work through it, and assuming I've done everything correctly, this is our information matrix. Okay, and then of course, if we want the expected value of this, then we get basically the same thing, but the expected value of mu is of mu hat here is just mu, but so we come out with this. Okay. Well, now we have, we're going to replace mu, the one parameter, with two parameters. Okay. Right? Because we're going to be using this linear function beta naught plus beta 1 times x. Now, what's adding an additional wrinkle here is that the way that we parameterized our model is that our linear model here is not describing mu, but rather the logit of mu. Okay, so it's the log of mu divided by 1 minus mu. Okay, and so our linear model is actually describing this. Okay, not just mu. And sometimes I'm going to use the eta the eta symbol here to represent the entire linear model when it maybe shortens the notation a little bit. Okay. So what does this mean? So now we're going to have parallel equations going, right? So here we just basically manipulated functions of mu, but now we're going to have functions of beta naught and beta 1. So we're going to have these parallel equations, for these guys. Okay. So maybe the first thing that we can do is to derive the expression for mu. Okay, because this is, right, we have this equals this. So maybe we can find what mu is, okay? And in fact, we can go through that derivation here, right? So we have this. Here I'm using capital X, or bold X beta as representing the entire linear model here, okay? But when you run through this, not derivation, but when you try to isolate mu, you take you exponentiate both sides, and you have mu 1 over mu, and then you can take 1 minus mu over and just follow the derivation. But anyway, you come out with mu equaling something like this right here. Okay, that's what mu is. Okay. Well, now that we have mu, we can just plug our expression for mu into what we did earlier in the simplified version. Okay, so here's our log likelihood in terms of mu, and now we're just substituting our expression for mu in there. Okay, and I'm also simplifying it even further by using the eta function. Okay, just for a little bit, just to cut down on my typing and just to make it a little bit more legible. Okay. But we run through all of this derivation, and eventually we get to here. Okay, so I won't go through the steps. Hopefully you can do that for yourself and tell me if I've made an error. But now we just take the eta symbol and plug back in our linear model. Okay, and so then this becomes our log likelihood. Okay. And so now we need the score functions. Okay. So because we have two parameters, beta naught and beta 1, we need the derivatives of the log likelihood for both beta naught and beta 1. Okay, so these are partial derivatives, right? We need the partial, so the score function for beta naught is the partial derivative of the log likelihood with respect to beta naught, and the score function for beta 1 is the partial derivative of the log likelihood with respect to beta 1. Okay. And so, again, I won't go through all of the steps here, but you can go through it, and again, tell me if I've done something wrong. But in the end, the score function, that is to say, the derivative of the log likelihood with respect to beta naught is this guy right here. And similarly, the score function for beta 1 is this guy right here. Okay. I should say, so here apparently I ended by putting it in terms of mu. But mu is just this, right? So of course, this expression and this expression are the same thing. Okay. And here, I'm not exactly sure why I did it like this, but here I converted it back to to the expanded formula. Okay. So now we need all of the partial second derivatives, okay, for our information matrix, right? And so our information matrix is going to be in terms of partial derivatives. So I'll probably just say derivative instead of partial derivative, but we want the partial derivatives. Okay. So it's the derivative of the score function for beta naught with respect to beta naught with respect to beta 1, and then along the bottom row, the score function for beta 1 with respect to beta naught and beta 1. Okay. So, so again, assuming I haven't done anything incorrectly here, I just go through and I just get the derivative, or so first I expand everything out, right? So I want the partial derivative of this expression, and this was just the score function for beta naught. Okay, score function for beta naught now with respect to beta 1, and then down here these are the score functions for beta 1. Okay, all right, and then the derivative with respect to beta naught and beta 1. Okay, and then we can go through and evaluate all of that. Okay, so we evaluate all those, and hopefully we get this and this. Okay, so in the second step here, notice that I've taken all of these minus signs and just put it out front as a scalar. And so now we have that out front, and these derivatives happen to be negative, so it all becomes positive. Okay. Now, so these are the derivatives here, and so so notice then that they all have this term right here, this fraction in common. So I'm just pulling that out. Okay. And then what's left, in each of these is, just what's in the matrix there. Okay. Also, they're also, I'm pulling out the summation sign here. Okay. So, so let's kind of keep digging in because, okay, so right now this isn't quite recognizable as the thing that we're meant to prove, which is this, right? It doesn't quite seem recognizable, right? So we need to keep digging a little bit. Okay, so so let's examine this thing right here. Okay, now recall that mu is this expression, and so if I wanted 1 minus mu, I would just, that's what it would be, and now I can, I can kind of give these the same denominator, right? So now 1 can be represented by that, okay? And now because they have the same denominator, I can take this and this, right? And then I have, so now I have 1 plus this minus this, which just leaves 1, okay? So now I have an expression for mu and 1 minus mu. And so when I multiply those two together, I get the expression that's sitting out front here, okay? So in other words, this expression right here is just mu times 1 minus mu, okay? And so now, so our expression for the information matrix, I can just re-express like this, and then I can just push this summation of mu times 1 minus mu back into the matrix, and this is what we're meant to show right here. Okay? And again, we can take this one step further. We can take the expectation of this guy, but here, the expectation is just the same thing, right? It won't always be that way, but here it is. Okay. Okay. I think that is it for this one.